this problem, we're going to consider a wave function in the infinite square well. So if we have a particle in the infinite square well, it will have a wave function that can be expressed in such a form. And then what we want to show is that we want to define a certain time interval t, and we're going to call this the quantum revival time. And then what's so special about this t is that the wave function will actually repeat itself after every t interval. So what that means is that xi x of t would take on some certain form, and then after a period of time, capital T, your wave function will turn into something like this. And then what's so special about this particular value of t is that after such an interval, both of these wave functions will actually be equal. So the wave function will just return to its state at this particular time, and then it will just keep on repeating itself. So at a particular time point t, after time an interval of capital T, it will return back to its state at time t. And so that means when it skips ahead for another time interval of capital T, the same thing will happen again, because you're basically starting off at the same point. So at this point, your wave function looks like xi x t, and then at this point, your wave function also looks like xi x t, because xi x t plus capital T is actually equal to xi x plus t. So in the end, this pattern just keeps repeating itself. And so this capital T is going to be the so-called revival time. So what we're going to want to show in this video is that for a particle inside the infinite square well, the revival time is given by this expression. So what we want to prove is that this statement is going to be true for this expression of capital T. So what we're going to do is that we're going to start off with this expression over here, so t plus capital T, and then we're going to substitute it inside this expression. So we start off with have a constant Cn, and then we have the n stationary state, and we have e to the power of negative I en t plus capital T divided by h bar. And you can see that as time goes on, this wave function is going to change, and all the change caused by the change in time actually comes from this term. So I'm just going to focus on this term. So as time goes on, these terms, this constant Cn and the n stationary state, both of these terms, they don't change at all. So I'm just going to focus on this term. So I'm just going to pull this term out and see if it can tell us anything about what will happen after time skips ahead by an interval of capital T. So I'm just going to break this up into two parts. So I have negative I en small t divided by h bar times negative I en capital T divided by h bar. So what we're going to show is that we're going to show that this term actually is going to be equal to t. Is actually going to be equal to 1. So if I take this term out, we know that using Euler's formula, we can actually express this as cosine en capital T divided by h bar minus I sine en capital T divided by h bar. And then for the infinite square well, the energy level of the n stationary state is given by this formula, n squared pi squared h bar squared divided by 2ma squared. And so that means En times the time interval t is going to be this expression, so n squared pi squared h bar squared divided by 2ma squared, multiplied by the expression capital T over here, which you can see is equal to 4ma squared divided by pi h bar. And then if we cancel out some of the terms, you see that this cancels out. This gives you a 2. The a squares, they cancel out. And then one of the pi's, they cancel out. And then one of the h bars, they cancel out. So in the end, we have 2h bar pi n squared. And then inside the cosine and the sine term, we also divide this by h bar. So this en t is going to be equal to 2h bar pi n squared. And then you can actually remove the h bar as well. So in the end, this whole term here is going to become cosine 2 pi n squared minus I sine 2 pi n squared. And you can see that n actually takes on all values, all natural numbers. So n is going to be equal to 1, 2, 3, and so on. And so that means n squared is going to have to be an integer. And if you have 2 pi times an integer, and then you put this inside the sine function, this is just going to give you 0. So this whole term here is going to be equal to 0. And then for the cosine function, when n is equal to an integer and you have 2 pi attached to it, this is going to be equal to 1. So if you don't remember why this is the case, you can just take a look at the graphs of these two functions. For the sine function, so this would be 2 pi, and then this would be 4 pi. And then you can see that for all integer multiples of 2 pi, your sine function is going to be evaluated to 0. And then for your cosine function, it's going to look something like this. And so this point here would be 2 pi, and then this point here would be 4 pi. And so for all integer multiples of 2 pi, you would get 1 for the cosine function. So this is going to be 0, this is going to be equal to 1. So that means e to the power of negative I en capital T divided by h bar, this term is actually just going to be equal to 1. It's equal to 1 minus I times 0, so it's just going to be equal to 1. So that means this term here is going to be equal to 1. And so that means this e term over here, we can actually just completely ignore this term over here because it's just going to be equal to 1, so only this term survives. And so that means this expression over here, this expression that we have for the wave function, we can now express it in such a way. So let us just copy out the summation sign first. So we have Cn xi n x, and then we have e to the power of negative I en. And this time, instead of writing t plus capital T, we know that the capital T term over here is just going to be equal to 1, so we can just ignore it. So we only need to include the small t, and then divided by h bar. And then you can see that this term is actually just equal to xi of xt, right? So that means this is actually equal to xi xt. And so there we have it. We have proved that if t is going to be equal to this term, so 4m a squared divided by pi h bar, then this term over here is going to be equal to xi xt. And so that effectively proves that this value of capital T actually gives us the revival time. So this is the revival time for a particle in the infinite square well. So that's going to be part A of this question. Now in part B, we want to find the revival time for a classical scenario. So if we're dealing with classical mechanics, and then we also have an infinite square well, that means a particle is just going to be bound within this region over here. It's going to bounce back and forth on the x-axis, and then it's going to do so at a constant speed. So what you're going to get is that you'll see that for a certain energy level E, your particle is going to have such a magnitude of kinetic energy. So that means its speed given by V is going to be equal to 2E divided by m, and then square root. And so that means if we want to find the revival time, so remember the revival time is the amount of time required for the particle to start off in one state and then return back to the state that it started off with. So for the case of a wave function, that would be equal to the amount of time when the wave function returns back to its form at time t. And for a particle in a classical scenario, the revival time would refer to the scenario when the particle, let's say it starts from here, it's going to bounce over to this wall, and it's going to bounce back, and then it's going to be returned to this position. So it's going to return to the same exact state that it started off with. So the amount of time that it takes for it to return to its initial state is the time for it to bounce back and forth between this distance over here, which is given by A. So the revival time is going to be the time that it takes for this particle to travel back and forth within this well over here. So that means the revival time is a time such that when you multiply it by the speed, you're going to get 2a. So 2a is the distance traveled when you go back and forth. So when you go back, when you go by a distance of a and you go back by a distance of a, you would essentially return back to its initial state, and everything is just going to repeat itself again. So that's why t is called the revival time. And so by that reasoning, we get this formula for the revival time in the case of a classical scenario. And so you can see that since v is defined in such a way, we can just dump everything over to the other side. And then we will get a formula for the revival time for a particle in a classical scenario. So you can see that there's a 2 over here, there's a 2 here. I can just put the 2 over on the top. And so there we have it. This is the revival time for a classical scenario. And in part C, what we want to do is that we want to find for what energy level that the classical revival time is going to be equal to the quantum revival time. So the quantum revival time is equal to 4ma squared divided by pi h bar. And then for the classical revival time, it is going to be equal to a divided by square root of 2m divided by e. So you can see that for the quantum revival time, it's actually just dependent on the width of the well. While for the classical case, it's going to be dependent on its energy level. And here you can see we can just cancel this out, and I'm going to square both sides, so it gives me 16m squared a squared divided by pi squared h bar squared. On the right hand side, I have 2m divided by e, so m cancel out. This gives us 8. So you see that e is going to be equal to pi squared h bar squared divided by 8m a squared. And this is actually equal to the first energy level divided by 4. So the first energy level is what you get when you substitute in 1 for this formula. So you can just substitute in 1 for n, and then you will get your first energy level. And you can just divide it by 4, and you see that you will get this result. So that what this is saying is that in order for the quantum revival time to be equal to the classical revival time, the particle in the classical scenario should have such an energy level if the two revival times are to be the same.